Hello everyone, I am Sushil Verma, third year PhD student in Georgia Tech, and today I'm excited to talk about my work on near optimal control for ride hailing with strategic servers. This is a joint work with Professor Francisco Castro from Anderson School of Management UCLA and my advisor Professor Sivateja Maguluri. The talk is divided into three major components: the model, fluid analysis, and stochastic analysis. In the model part of the talk, we'll start with the basic built-in block of two-sided markets, a single link two-sided queue. Next, we'll extend this to a bipartite graph of a two-sided queue, and finally incorporate strategic settings into the model. Without further ado, let's jump right into the modeling part of the talk. A two-sided queue mimics a two-sided market of customer and service. To illustrate, consider that a customer arrives into the system and the system operator quotes a price to the customer for the offered services. Depending on how the customer values the service, it will either reject the offer and leave the system or accept the offer, pay the quoted price to the system operator and join the queue waiting to be matched. Similarly, a server may also arrive in the system. A system operator will quote a price for the services offered by the server. The server can then either reject this price and leave the system or accept the price, receive a payment, and join the queue to serve the customers. If there is a customer server pair waiting in the queue, the system operator can then decide to pair them up and they instantaneously depart the system, indicating that the service is complete. Such a dynamic will continue, and it may happen that a lot of customers have joined the system and are waiting to be matched with no available servers. If such a scenario occurs, then the experience of the customers will degrade due to high waiting times. To alleviate the waiting times, the system operator can offer a higher price to the servers so that it is now attractive for the servers to join the system. On the other hand, the system operator can also increase the quoted price to the customers so that the majority of future customer arrivals will not accept a higher price and leave the system. This highlights how the system operator can use dynamic pricing to manage the influx of supply and demand and set the prices, which leads to lower queue lengths and waiting times. This can be mathematically interpreted as follows. The customer and server arrival rates are dynamic and depend on the current state of the system, denoted by lambda of q and mu of q respectively. The system operator wants to set the arrival rates or equivalently the prices for the customers and servers such that the net profit it is maximized, which is defined as the revenue obtained from the customers minus the cost due to the payment to the servers minus the waiting cost penalty to ensure lower waiting times for the customer and servers. Now, we generalize the model to consider multiple copies of the two-sided queues with a compatibility graph between them. In the context of ride hailing, a type can be interpreted as a geographical location of the customer or the driver with compatibility depicting the geographical proximity. The system operator can only match a customer server pair that are compatible with each other. Due to such a compatibility constraint, the decision to match a customer server pair becomes non-trivial. For instance, consider the following state of the system. The system operator can match the server waiting in Q2 to a customer in either Q2 or Q1. If, for example, the system operators decide to match it to Q1 customer and in the next time slot a server of type 1 arrives, then it will have no compatible customer waiting in the system as we exhausted the customers in Q1 already. Thus, the current matching decisions will impact the future availability of customer and servers, which makes the matching decisions non-trivial. To summarize till now, we have a bipartite graph of two-sided queues with customers and servers arriving into the system with queue length dependent arrival rates, which is the pricing control as discussed previously in a single link two-sided queue setting. Next, the system operator decides which pair to match among the available matchings. The objective is to maximize the net profit, which is defined as the profit minus the waiting penalty as before. This is a joint optimization problem in the space of pricing and matching policies, and it was previously studied in the following paper. In particular, they propose a near optimal pricing and matching policy. In this work, we show that it is non-trivial to generalize these techniques to the setting of strategic servers. The system operator sets the price offered for all types of servers. Let's say a server of type 1 arrives into the system. The server may find Q3 and Q4 more attractive as the price offered is higher. In addition, Q2 and Q4 share neighbors with Q1, which makes them similar to Q1. Considering these observations, the server lie about its type and rather goes and joins Q4. In the setting of ride hailing, this is motivated by the service offered by Uber and Lyft that the driver can set their preferred destinations, which can align with them going home or going to school to pick up their kid, etc. To formalize, each server has a utility function that depends on the price posted by the system operator and an additional inconvenience cost. Depending on the maximum possible utility, the server decides to join the system and declare his type. We capture this complicated dynamics by judiciously defining a cost function. In particular, there may not be a one-to-one correspondence between the price and arrival rates. Cost function, defined as a value function of an optimization problem, allows us to deal with that issue and also provides us with a lot of flexibility to model different strategic behaviors. We will defer this discussion to the end of the talk. To summarize the model, we have a system of multiple linked two-sided queues with strategic servers. The system operator needs to design a pricing and matching policy that ensures equilibrium and also maximizes the net profit. Now, we'll solve this problem by first considering the fluid model. We will begin our discussion by considering the classical fluid model considered in the literature, where the stochastic quantities are replaced by their expectations. This results in an optimization problem of maximizing the profit subject to balanced arrival rates. In a single link queue, this boils down to expectation of lambda is equal to the expectation of mu, which intuitively is a first order condition for stability. In a multiple link two-sided queue, balanced arrival rates corresponds to an existence of a matching which matches the customer arrival rate with server arrival rates exactly. A key observation we made is that such a fluid model may not guarantee to provide an upper bound on the maximum achievable net profit under a stochastic pricing and matching policy. This is mainly due to the non-convexity of the cost function. In particular, the equilibrium constraints that are used to define the cost function leads to non-convexity. Due to this, Jensen's inequality may be violated, which can be interpreted as the existence of a probabilistic pricing policy which results in a higher profit. Motivated by this, we convexify the objective function by considering the space of probabilistic pricing policies for the servers, and the new optimization is in the space of the probability measures that define the pricing policy. We call this the probabilistic fluid model. An interesting observation is that the fluid model partially preserves stochasticity as opposed to the deterministic fluid model considered in the literature. With this convexified probabilistic fluid model, we show that it provides an upper bound on the achievable profit under any pricing and matching policy. Now, we point out the key differences between the probabilistic fluid model and the classical fluid model, which shows that the probabilistic fluid model is more general. Fluid model is a deterministic optimization problem, whereas a probabilistic fluid model preserves partial stochasticity. Next, a fluid model may be non-convex depending on the original problem, whereas a probabilistic fluid model is always convex irrespective of the original problem. Fluid model provides an upper bound on the achievable profit for any stochastic policy only if the cost function is convex, as opposed to probabilistic fluid model providing the same guarantee for any cost function, which is important to analyze the strategic behavior. Lastly, the fluid model results in a deterministic optimal fluid policy, and the probabilistic fluid model may result in a probabilistic optimal policy. This concludes our fluid analysis. Now, we'll work with the stochastic model and provides an asymptotically optimal pricing and matching policy that also ensures equilibrium. The recipe of the stochastic analysis is as follows. Solve the probabilistic fluid model and perturb this solution to optimal. The motivation for perturbation is that operating close to the fluid optimal policy results in a superior profit, and the perturbation of the policy introduces dynamic component which ensures lower waiting times. Lastly, for provable guarantees, one needs to show stability of the underlying system, optimality of the proposed policies, and that the system is operating in an equilibrium. We propose a perturbed probabilistic two price policy by perturbing the customer arrival rates and a max weight matching policy that matches a customer to a compatible server with the highest queue length and vice versa. To show optimality of the proposed policies, we consider a large market regime in which the customer and server arrival rates are sped up by the parameter eta. And we show that our proposed policy only loses an order of eta power one third in profit compared to the upper bound provided by the probabilistic fluid model. In addition, we show that a wide range of pricing and matching policy will lead to at least eta power one third loss in profit. This proves that our proposed policies are asymptotically optimal and also achieves an optimal rate of convergence. Before concluding the discussion, we would like to point out the generality of our framework. In particular, the cost function can be easily modified to encompass different strategic behaviors. For example, we can study the profit maximizing policies, which takes into account the strategic behavior and ensures that the net profit is maximized. In addition, we can study the incentive compatible policies that ensures that the prices are set such that the servers join their own queue, or a partially incentive compatible system which ensures that at least a given fraction of servers joins their own queue. Lastly, we highlight that the case of no strategic behavior can also be included in our model, which points out that this framework is a generalization of the earlier non-strategic setting. We also consider multiple extensions of our model, and please refer to our paper for more details. Now, we will discuss the intuition behind the asymptotic optimality of the proposed policy. In particular, the intuition for eta power one third loss in profit and the fundamental reason behind it. An epsilon perturbation of the fluid solution results in 1 by epsilon order of expected queue length and eta epsilon square loss in profit. Considering the trade-off between the two terms, we should pick epsilon to be of the order of eta to the power minus one third, which will result in eta to the power one third loss of profit. This is the fundamental reason. Now, we will understand each of these terms separately. The expected queue length is of the order 1 by epsilon. This is because in spirit, a two-sided queue operating under an epsilon perturbed policy is similar to a single-sided queue operating in heavy traffic with epsilon as the heavy traffic parameter. Intuitively, the drift towards zero for the two-sided queue under an epsilon perturbed policy is of the same order as the drift towards zero for a single-sided queue in heavy traffic. It is well known that expected queue length in heavy traffic for a single-sided queue is of the order 1 by epsilon by Kingman's bound, and thus we get 1 by epsilon order of queue length for the two-sided queue. Next, to gain intuition for the loss in profit, denote the profit function, that is the revenue minus the cost, by P, and the fluid optimal solution by X star. We can use Taylor series expansion to write the profit under an epsilon perturbed stochastic policy in terms of the fluid optimal profit as follows. Note that the first term in the right hand side is the fluid optimal profit, and the term after that is the first order term which vanishes due to the optimality of X star. Thus, the loss in profit is of the order eta epsilon square. To summarize the previous two observations, for the ETAT system in the large market regime, the expected Q length is of the order 1 by epsilon, and the loss in profit is of the order eta epsilon square. We can similarly analyze the original system with no asymptotic regime given that epsilon is small enough. This will result in 1 by epsilon order of Q length and epsilon square order of loss in profit. Using this, we can state the following result. Suppose we impose a service level constraint, that is the expected Q length must be equal to C for some positive C. Then the profit that can be achieved under any such policy will be at least 1 by C square order less than the fluid profit. This is because to achieve expected Q length equal to C, we must pick epsilon to be of the order 1 by C. Thus, epsilon square is of the order 1 by C square, which indicates that the loss in profit is of the order 1 by epsilon square. This result can be employed in practice to understand the trade-off between the profit and expected Q length. To summarize, we present a two-sided queuing model incorporating strategic servers using a judiciously defining cost function. Next, we propose a novel probabilistic fluid model which provides an upper bound on the achievable net profit under any pricing and matching policy. Lastly, we present a recipe for the stochastic analysis and present an asymptotically optimal pricing and matching policy. Thank you for listening to this talk. Feel free to reach out to me if you have any further questions. I would be more than happy to discuss. Thank you.